the squeeze, just, you know, it's like a no-op if it's not needed, and then it will do the thing if it's needed. So at this point, I'm kind of confused. I'm sure at some point we had to deal with this, and I don't recall when or what, you know, like under what circumstances. So if you had no problem, but if you did have a problem, what Gurnoff pointed out, like in that line, adding the dot squeeze 1 will solve the problem. And hopefully, at this point, you've learned a little bit of PyTorch, and maybe if you run into the problem, you might diagnose it and see, you know, and see that as a potential problem if you have dimensions without any data in them. Okay. Homework 4 is due today. End of the day. A lot of you have already turned it in. So yeah, I will be here after the lecture if any of you want to talk about the homework. Other than that, hopefully it's gone okay, and you're just going to get it turned in. On project proposals, almost everybody has their project approved. There are just a couple where the group hasn't responded to my comments, and I'm sure none of you here in the actual room physically, I'm sure that's not the case, but perhaps there's somebody listening, and just know that your project is not approved until I have said in those notes approved, and you get your 1 extra point for that. So yeah, please look into that. If some people have wondered where the comments are, if you're still wondering, you just, you know, go to where you made this submission, and there is, you know, in Canvas there are some dialog boxes for or there's some text boxes for communicating back and forth, you know, entering comments, and so it's just there. Hopefully you'll see that. If you don't know, if you don't see it, send me an email. Yeah, any other questions before we get started? Cool. So, this week's going to be our 1 week for reinforcement learning. So this is just another kind of machine learning, like the large category or you know, like large family, this division of learning. We've learned about supervised learning, where we have labels and we're essentially learning a function from the data to the labels. We have unsupervised learning, where we just have labels and we're learning something about the structure of that data. And now we have reinforcement learning. This is very different. There is a kind of learning going on, but the way that these kinds of learning problems are framed is that you have one or more agents that are in an environment, and they follow policies to respond to the state of that environment. And they can take they can make different kinds of decisions or different responses to that environment. And they learn by being rewarded for the actions that they take. That reward can be a positive, you know, reward, or the reward can be such that it's you know, pointing you, like teaching the agent to do actions like that, and the reward can be such that it's teaching the agent not to do actions like this. And in general, the way that these learning problems are posed is that we are taking actions to maximize our rewards in some sense. So yeah, so it's neither supervised learning nor unsupervised learning. It's something different called reinforcement learning. And the idea of using the word reinforcement is that the reward is reinforcing the behavior that you want the agent to have. 1 second. Okay, so are lots of cool examples of this. I have some old Atari games, and like, I'm old enough where I had an early Atari and played these games before computers played them way better than any human could. And this is one of the like early, or one of the common playgrounds in which reinforcement learning agents are trained, and where like a lot of research happens. But there are many other venues as well. Oftentimes, though, they are games, and we'll go through some examples. But games, because games are very well structured, they have structured environments. You have structured agents. You know, like the agents are the players, and there's usually a pretty well structured reward system. You know, through scoring in some ways. What we're going to be learning today is just learning a bit about what reinforcement learning is, how like the math or theoretical setting for reinforcement learning, something that's known as Markov decision processes, and we're going to learn about Q learning or deep Q learning, and that will be the content of the day. So, really simply, reinforcement learning is there's an agent in an environment, and the environment provides, you know, the environment sort of determines the state, and that state is indexed by time. There's a kind of temporal, you know, index here. We are there, you know, the environment's in a certain state, and the agent responds to that by taking an action at that same time. That may or may not change the environment, it changes the state of the, you know, of the environment, and we sort of just like move forward in this process of agent in a certain state takes an action, now is in a new state, a possibly new state, and now takes another action, so as to maximize reward. So when it takes that action, whenever it takes that action, there's typically a reward given or provided to the agent, and this is the signal that is used for learning. And we're going to go through a bunch of examples here, but this is the signal that is used for learning. So, you know, because this is a neural networks course, you know, expect there to be some way of representing, you know, rewards and how they're obtained through neural networks in response to, you know, actions and taken in certain states. But there's a sort of temporal, you know, sequence to this. So, agents in a state at time t takes an action given that state. There's a reward given. That could be, you know, that could be a reinforcing a reward, or a reward that is meant to deter that action being taken in the future. It could be no reward at all, because possibly the reward is going to be given later on after a sequence of actions. And then we're in a new state, and we just kind of keep going in this sequence. So classically, in like reinforcement learning problems, or reinforcement learning, when people were studying this kind of for the first time, I suppose, you know, before there were like all kinds of great video games and things like that, and easy ways to simulate these kinds of environments, there were like physical problems that were used to as the environment, or as like the prototypical problem for training reinforcement learning agents. And the classic one is the cart pole problem. Anybody ever seen this in like their physics course? Have to like solve this problem. The idea is you have this inverted pendulum on a cart, and you know, if this is standing straight up, and say there's no force here, this thing is at equilibrium, meaning like it should stand straight up. But you know, as soon as there's any sort of perturbation from that equilibrium, it's going to fall. It's an unstable equilibrium, and like the pendulum's going to fall just due to gravity. And the object of the cart pole problem is to apply forces to the cart, which in the simple, like 1D case here, it can move to either to the left or the right, so as to keep the pendulum standing upright, never to fall down. So it's kind of always wanting to fall, unless you can get it into that like perfect unstable equilibrium. It's always wanting to fall, and therefore, you now have an opportunity to move that cart to keep it standing up, and it's when you play this game, it's some kind of wild back and forth of just keeping it straight up. But the state of this is pretty simple to describe, right? You have your position, on this like one-dimensional track. You have an angle describing how inclined this inverted pendulum is from the vertical position, and you have just the position. Well, not the position. So this describes entirely the position of like this mass up here, but then you have also the forces that one could apply. So you have that angle. You have the speed at which that mass is falling on the pendulum. You have the position on the track, and you have the velocity as created by the force. And again, the idea here is you want to keep this pendulum standing upright. So if you were to turn this into a reinforcement learning problem, you basically want to reward this, some agent that's learning to do this for keeping the pendulum upright. So some really simple way to do this, right, is to give some kind of reward, say like a reward of 1, whenever the pole is upright, and not necessarily vertical, but just like, above horizontal, and then, 0 or maybe something very negative when the pole is laying horizontal. And so the actions that it can take, right, is apply this force, and so, given an appropriate kind of learning algorithm, we haven't talked about the algorithms here, but just an appropriate learning algorithm for this problem, you should be able to train or teach agents to apply forces so that you keep that upright. But pretty quickly, that became a really boring problem, and we needed like way more interesting problems. So we got lots of interesting problems. So this is one that is of interest to the classical AI community in general. This is the idea of robot locomotion. Like if I have a robot, of any kind of design, it could be humanoid, it could be something else like this kind of arachnid one. Like how do we give it instructions to move? It's actually a really hard problem. I mean, I don't know if any of you are into robotics, that's your major or whatever, but if you think about it, it's one of those hard problems. How do you like write the program to say this is how you, like if I'm a humanoid robot, this is how you walk, or if I'm this arachnid, this is how you move left, move right, turn around, things like that. What does that look like? And one way to approach this is through actually rewarding it, letting it learn to move, to actuate the motors, and reward it for like actually moving in the right direction, standing upright, those kinds of things. And it's that could be very expensive if you're doing this for an actual like physical robot. But if you could do this in simulation, like what these are right here, then maybe you can learn to do all that movement, in simulation, and then transport that learned policy to your robot. And that's how a lot of reinforcement learning, especially earlier reinforcement learning, looked like this. And so this is actually, we're going to watch this kind of a series of videos here. Hopefully there's not going to be too many ads. Okay. I know we don't have, hopefully you'll be able to see this. This is a bit old now, but It's pretty interesting. So what we have here are demonstrations of these simulated robots after they've learned how to walk via reinforcement learning. So I don't know if you're paying attention to what's being said, but nothing about walking or anything was no instructions were given. There's simply the actions that can be taken through, like, bending the joints, basically bending the joints with some physics engine, and then there being a reward that is, if I start at point A, the closer I get to point B, the more rewarded I get. And so like these behaviors that you're seeing are simply learned through that kind of simple process. Yeah.
Sometimes you see the guy with arms as well. Were the arms part of it as well? And
Yeah.
Impact anything, they just went crazy?
Well, they don't just go crazy because the thing, it's like a physics engine, so it's going to fall over. Like if it were to like put both its arms over here. So the things that you see, like we walk in a certain way that hopefully we look cool when we're doing it, or whatever. But it's just it's just a way of doing it. Probably like a low energy way in general, doing it. But what you're going to see is, you're going to see some of these kind of crazy walks that nevertheless work in terms of being able to get from point A to point B. That were just sort of discovered as a part of like this learning process. And you're also going to see like the learning process. So let's keep going here. I like that one. So you see the environment. The environment, it's the different floors and the walls and other the other things that are blocking it. maybe you're gonna wow. So maybe you'll want to walk like that.
M&M's minis.
Thanks, M&M's. So so this is, when you all walk out of here, choose a new way to walk. Discover a new way. Reward yourself for getting to your car. Through new ways. So like, it's interesting to think about it. Like, really, again, what's happening here? These agents are learning to get from point A to point B within the environment, or like the state space that they're given, right? So what's the state? Well, you have, the simple way to think about this is just where are all the joints, and for each of those joints, what, essentially like what position is it in? Like what angle is it making with some reference frame? All right, and so like, the arms, whether or not there's elbows and things like that in the legs, also bending at the torso, rotation like that. What actions can we take? Well, we can adjust those. We can adjust those angles, right? So that looks like a force, like a torque on on those joints. And then simply we reward it by here's a simple way of rewarding it, giving it at each time step a positive reward, something like 1, when it's both upright and it's moved closer to the to the final destination, or moved forward further away from its initial location. So all of what you just saw were behaviors or policies, as we often call them, for accomplishing, for maximizing the reward here, which meant we got some kind of robot from point A to point B. Okay? Let's see. Atari games. So something very similar here. Games are nice because they typically have a kind of reward system built into them already, right? The score. Oftentimes you want to maximize that score, right? Could you put your initials, on the video game console down at 7-Eleven or whatever. My initials are BAE, Bay, and that became like a interesting thing. I remember when first time I discovered that, I was like, oh, cool. I was embarrassed, but anyways. So yeah, hopefully my initials are somewhere still at 7-Eleven where I grew up in California, but probably not. But anyways, you have these scores, and the action space, like the environment and the actions that you can take are really, they're usually, they're always well defined, and they're usually very simple, right? Especially for these kinds of games. Of course, the game can get more and more complicated, especially for these kind of Atari games, you have simple things like whatever, like the simple joysticks could do, right? Moving left, right, up, down, maybe pushing an action button, maybe two different action buttons, whatever. And the idea is that you want to maximize the score. Oh yeah, and the state, of course, is like all the pixel values at that point in time. So this is kind of cool because it's already pointing us towards like using convolutional networks to be able to understand and work with these kinds of state spaces. So what does this look like? We're going to get another great ad.
Hello, I'm Patrick
All right,
Stewart.
Patrick.
Did you know that right?
Nope. All right. Here we go. We get it in French as well. That's great. Okay, so here's some more research from DeepMind. We're gonna watch this thing play Breakout. Anybody know what Breakout is? No?
Is that where you're sliding?
Yeah. You'll see it here.
Oh yeah.
So you have this little paddle here, and the idea is you're trying to hit this ball, whatever this thing is, this little ball up into this like surface up here, and every time you hit the thing, I think it was a bunch of blocks, and if you hit one, you break the block. And the idea is you're trying to like keep doing that until you break a space all the way through and the ball goes on the other side. So what this is showing you is the process of using reinforcement learning to learn to do this. So at the beginning it wasn't doing very well at all, right? It'd break like one brick and then lose the ball or whatever. After now training for a lot longer, it's getting better, right? It's like keeping the ball going. This is saying after, I don't know, what's that, 4 hours of training? It's getting so good that what it learns to do is it learns some cool strategies. That strategy right there, that every good breakout player knows, where if you get the ball to the other side, it will just get rid of all the bricks on the other side because it'll bounce against the complete wall on the other side. So yeah, that's pretty cool. Again, simple reinforcement learning, like maybe a more complex state. Whoops.
At DeepMind, we basically work.
That's Demi, the CEO of DeepMind. So
a question on that. So
yeah.
In the game state, it knows the ball location just in like X, Y coordinates.
Well, it doesn't really know the ball location. What it knows is the pixel values. That's the state. That's actually an interesting point. Like we don't actually, in doing this, like in Breakout, we don't actually give it like the X, Y coordinates of the ball. The state is the whole every pixel, like that this whole image at time t, right? And when it takes an action, yes, like the action is actually to move, this paddle here, right? But it's not like it's got this causal model of like, I move it and that paddle moves to the right. It will learn something like that. But it basically, when it takes an action, all it really knows is, if I take this sort of sequence of actions, when the pixels are in this state, that I will like get a higher score. That's really what it knows. It does not have a model of the ball or the paddle or the bricks or anything else. It just has all the pixel values at each time. That's a really excellent point.
Kind of along that same
Yeah.
lines. Does it know the score, or is it?
Yeah.
Okay.
Well,
Is it like reading the score? On
it knows the score in the sense that it's getting rewarded for increasing the score.
Okay, so it does.
I mean, it doesn't, it's not given the score, you now have 1,232 points or whatever, and then, when I take this action, I have 1,233. It just gets rewarded if when it takes that action, that score stays the same or goes up. So it's a little bit different than actually having, keeping that in the state. Does that make sense? Yeah, it's not part of the state. I mean, it could be part of the state if it's, if those pixels are taken into account, but it's not, yeah. Okay, cool. So a little bit more complicated. Okay, Go. We talked about this at the beginning of the course. Games like chess, most board games with sort of really like recursive kinds of state spaces became a really important playground for reinforcement learning. And Go was up until 2016 when a reinforcement learning agent beat the world champions, like the grandmasters in Go. It was really thought that this would be a game that machine learning would always really struggle with, because you're rewarded in Go, you're rewarded by winning the game. Well, in all games, you're rewarded by, all games like chess and things like you're rewarded by winning the game. But that could be many, 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 many moves in the future, right? So, how can this, how can a machine learning system learn to appropriately credit the past actions in such a way that it would learn to play at a grandmaster level with just this simple kind of reward? And the answer to that is, well, it's a combination of very powerful models that can store a lot of state, but also very clever ways of training the models. And we're not going to go into that today, how the AlphaGo was trained, and then the various iterations of AlphaGo after that. There was Alpha 0, and there was Mu 0. Each of these removing more and more of the sort of built-in information about how the game is played, but always becoming grandmaster level players. But it's a combination of good training techniques, clever ways of creating data to be trained on, and very deep models to be able to keep all this state. And of course, some clever ways of in games like this and like chess, of thinking about the parameterizing the possible actions that the agent could take. We won't watch a video on this because it's it'd be a pretty long video. But in very much the same way that you just saw these other simpler games learn to be played, a reinforcement learning agent learns to play Go by learning to keep track of state, learning which actions to take so that we maximize reward, which is to win the game. There doesn't just have to be one agent, there can be multiple agents, either working cooperatively or adversarially. This is a really cool example from a few years ago. of agents learning to play the simple, childhood game of hide and go seek, which is a good, watch this video here as well.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if
Can you hear it
comparably
okay?
simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world. These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter.
Bug in the code, but
In the last stage of emergent strategy that we observed, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other, as well as past versions of themselves, using an algorithm called self-play. Coevolution and competition on Earth led to the only generally intelligent species known to date, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction. We hope that with a much larger and more diverse environment.
so anyways, they wax philosophical there. Really cool, right? Like you got multiple agents, each one of them with their own policy, with their own way of responding to the environment, but they're rewarded in similar ways, and so they learn to cooperate. And you saw kind of all these complex behaviors that came out of it. Again, there's really very little if at all, initial programming in here to all these policies. These policies essentially start out kind of random, and instead it takes thousands of times of playing. It really takes millions of times of playing. And this is one of the problems with reinforcement learning, that it's so what's known as sample inefficient. It requires so much data to be able to so much training on that data to be able to get to the point where the agents have learned to do something like maximize the reward. But again, it's pretty simple, right? It's as long as you can explicitly define your state and the actions that can be taken in each state, and the reward for the different actions that can be taken there, which even though of course this could sound really complicated, but in general these are fairly simple things. They're very explicit things to be able to specify and write down. As long as you can do this kind of thing, then you should be able to use the algorithms of reinforcement learning to maximize this reward and get all kinds of really interesting behavior. And of course, we're talking about games because this is a fun and intuitive way to think about these things. But reinforcement learning has been used for all kinds of really interesting applications. One that is really interesting is you know, Google, before it was Alphabet, bought DeepMind for like $600 million or something like that, and went on to like take massive losses to allow DeepMind to, you know, to learn to be, or to become, you know, like the real kind of powerhouse AI lab that it is. But one of the very first things that they actually did with reinforcement learning was to model like all of like the energy consumption at Google's campuses, you know, like in their buildings, and come up with optimal policies through reinforcement learning for, you know, like maximizing, you know, some reward, which is like to keep the temperature, you know, at some sort of comfortable constant state while minimizing costs. And it was like super effective. And I doubt that they saved, you know, $600 million or something like that. But they did save like millions and millions of dollars from, you know, after buying this AI company. It's kind of, it's interesting. It's a very general way of thinking about like machine learning and setting up problems in which, you know, you're trying to learn an optimal behavior, but as often is in machine learning, how you would explicitly program that is like, you know, beyond our capabilities. Okay, cool. So that's a little setup, a little bit of, you know, some interesting examples. There's so many more. There's just so many cool examples there, but how do we go about like thinking about reinforcement learning problems? Like, how does this end up getting turned into an objective that we're trying to optimize? So reinforcement learning is actually quite like an old idea. It's been around for many, many decades. And so a lot of the theory here has also been around for that long. And it's only been recently where you know, deep learning or neural networks have been introduced to certain aspects of this theory to allow for there to be much more powerful agents, to learn much more complex and nuanced policies. But what does this look like? Well, this is all set in what's known as Markov decision process theory. Anybody seen this before? Anybody here? Yeah? Is that because you're like in economics or something like that?
I took the AI class recently.
Okay, cool. Others seen this before? Yeah? Same thing? Yeah, okay. Cool. So this is a fairly general way of formulating the mathematically like the problem that reinforcement learning is trying to solve. So a Markov decision process has a bunch of like things to it. It's defined in the following way. You need to have all the possible states defined, right? So think about Atari. This would be like all of the ways that pixels can be arranged in a valid breakout game, you know. So that's a huge state space. And you know, think about Go. Think about more complicated video games. Whatever. It's like, you know, as long as you know. What you need is some way of being able to describe all of those possible states. So even if it's complex, even if they're like way more than you can possibly enumerate, as long as you can like, you know, you have some way of being able to describe each state, then we're good. So you need to have a set of all your possible states, and then a set of all the possible actions that you can take in each of those states. So like the union over all the possible actions from each state. And then you need some kind of reward that you'll give, and oftentimes this is like in the most general theory, this is described as a distribution of rewards, meaning that you might let's see. Well, so okay, so what we need is a reward that's given for every state and action pair. So why the pair? Well, you have an agent who's in a particular state and could take one of many actions, and then you need a reward that for each of those. Now that reward could also be, you know, probabilistic. but in general, you need to have some kind of notion of how to give rewards given the state of the environment and the action that the agent takes in that state. Oftentimes this is very simple. Of course, this could get very, very complex. And then you need some kind of way of saying, how do we move from one state to the next, given the action that's taken. So this is in its most general form, given as a probability distribution over all the possible states given the current state and the action that's taken. So again, there's like some notion of probability allowing for there to be, randomized responses. That doesn't mean like that they're like uniformly random, like there's no information given, but that the way that the environment responds can vary, given some whatever this distribution might be. So states, actions, rewards, ways of transitioning from one state to the next, right? That gives us our sequences, given the action. And then we have this funny last thing here, the discount factor. Why is there a discount factor? Well, we'll get into that in a second, but the discount factor is a kind of really like a mathematical device for being able to express the weight or the relative importance of rewards that that were obtained at different time points, and we'll kind of see that mathematically how this shows up. But really, what's in general, what will have happen is, as this will be a number between 0 and 1, and we will weight decisions or actions that were taken in the past by gamma to the however many time steps that happened in the past, or actually more appropriately in the future. Sorry, I kind of got this backwards. We're gonna discount rewards that we could possibly take into the future. Sorry, I got my times mixed up here. Which direction we're going? Anyways, we'll see the formulation for this mathematically here in just a second. But we have this kind of additional thing, and then this whole thing is called a Markov decision process. And Markov, in math and related theoretical subjects, is when you say something has the Markov property, it's this important property, at least mathematically, because it allows for us to decouple ourselves from the past. And basically it's saying the Markov property is that the current state that we're in at time t completely characterizes the state of the world. We don't need to keep the state from previous time steps, for instance, to be able to make the decision that we're going to make, like which action we're going to take. We just the state of the world now is all the information that we need to be able to make a decision in the future. And mathematically, that just makes everything a lot easier, and it's also pretty reasonable, right? I mean, we could violate this pretty easily in real life, but it's fairly reasonable that agents will just use what information they have now to make decisions. Okay, so a little bit of theory there. So what does this look like? Well, we use these objects that are in our definition of the process to create the sequence of states and actions. So how does that work? So at our initial time step, so we'll call that time 0, we need to be in an initial state, and we had this distribution over states, so we can imagine kind of sampling from that distribution. So so that gives us an initial state. And then once we have an initial state, we just run this loop, and this loop is, given the state, the agent selects an action. The environment like provides or gives a reward given the state and the action. The environment updates itself, again given to a new state given the state and the action. And that agent receives the reward and moves into the new state. Okay? And remember that these were thought of as probability distributions. So these could be deterministic in the sense of like there's only one possible reward that could come from this state action pair, or one possible state that could follow this state action pair. But in general, it could be there could be some randomness here, and so we're sampling from a distribution. Okay, so like again, it's just like a way of sort of formalizing this whole notion of what's an agent doing in this environment and how do things get updated. Okay, so what? Well, what's the big deal? Well, the big deal here is that in a Markov decision process, what we're trying to do is learn optimal policies. Now, what's a policy? A policy is the agent's decision-making process. It's what the agent uses. It's this function that takes us from the state we're in and produces the action that we're going to take. Right. So it's a function from the state space to the action space. That's a policy. So it's given this state, what action will I take? And the objective here is to optimize that. We want to find an optimal policy somehow. So how are we going to do this? Well, there's a lot of ways you could think about this. There's a lot of ways that you could, there's a lot of things there's a lot of objectives you could optimize, but the one that is used for most of the theory, especially for Markov decision processes, but also for a lot of the ways in which we formulate reinforcement learning objectives, is this cumulative discounted reward. So what is this? Well, it's this series right here. So, as the agent acts in this environment, it's receiving rewards, right? And a reward at time 1, time 2, time 3, time 0, time 1, time 2, and so forth. And we could think about maximizing that, just like the full sum of those rewards. But there's two problems. One is, mathematically that series will typically not converge, so we need to make it converge. And how do we make it converge? We use this discount factor. And so this is really, it's a mathematical trick. It's putting this value between 0 and 1, as a coefficient here in front of each of the rewards, and then raising that to the teeth power. So the justification for this, psychologically, is that rewards way out in the future from where I am now, at time 0, sort of have less importance to me than rewards that'll come sooner, like in the next step or in a couple of steps. And this, and this factor is a way of expressing that. The smaller this gamma is, the less important the rewards in the future that I might obtain are. The larger it is, the more important they are. But importantly, because this is a value between 0 and 1, and we're raising it to the teeth power, if you remember your calculus class, as long as this series is bounded, meaning that there's our rewards can't blow up to infinity or minus infinity, then this thing is going to converge to typically converge to a finite number. And that allows us to do math. So that's why it's there. So this is the thing. This might seem really kind of weird, You know, it always seems weird to me every time I look at it, but this is like the objective. We're trying to optimize this. We're going to be learning policies. We're going to be trying to learn policies that maximize this number right here. And basically, like, the whole of reinforcement learning is based on that idea. Yeah.
So gamma is constant here.
Yeah.
And the important part is when t is increasing, the gamma is effect on reward decrease.
Yeah, gamma to the t, that coefficient gets smaller and smaller and smaller. So, you know, many time steps out in the future, that's going to be really small. So even if the reward is really large out there, that number in the sum is going to be small. So it's, you know, what this means is that nearer term rewards are more important. But like the larger the gamma is, the more important, you know, future decisions are.
The larger the gamma is, all of the rewards are important equal.
Yeah, I mean, except that it's between 0 and 1. So eventually, you know, there will be a large enough time step where those rewards won't matter anymore, right? It's just the mathematical way that this is set up.
And what is the top bound of this number?
Of gamma?
No, this cumulative discount reward.
Oh, well, we don't know in general what it will be. This will depend on the values that the reward can take on. But as long as those things are bounded, this thing will converge.
It could be t times r.
Yes, but that wouldn't be bounded, right? Right, because that, like t, like if you have r constant and then times t, that's gonna, those rewards are gonna grow to, you know, infinity, right? So we're not gonna allow for things like that. We need the rewards to be bounded so that converges. Yeah. So at this point, it's all just kind of mathematical. It's like set things up so that we can do math, even if it isn't like the perfect model of like how decisions are made. Good questions, yeah.
Are rewards typically modeled as a distribution for every state action pair, or is it a direct function of state action pairs to?
Yeah, I mean,
does it matter?
you can do both. It doesn't matter. Like the only thing that changes here is, you know, like if it's direct, as you said, or like deterministic, there's just going to be a single reward that you would get given the state in action. But if it's not deterministic, then, you know, it can be very concentrated around like some mode or something like that. But you know, in the end, like all the math kind of works the same way. Any other questions? All right. So what do we do with stuff like this? Oh, right. Simple grid world. This is the toy problem essentially for reinforcement learning. If you go and if you go and look at reinforcement learning papers, oftentimes this is like grid worlds are you know, like the toy environments, the toy problems that you test an algorithm on, you know, to kind of show how it behaves or whatever in a very simple setting, and then you often port that over to something far more complicated like your video games or whatever. But grid worlds kind of look like this in general: 2D grids. The state, the states of this world are, you know, it's all these grids. The grids might be, you know, might have certain characteristics, in addition to just being a place where the agent can be. But it's, you know, but it's also it's the locations in the state space and then where the agent is. And then actions are, you know, typically just these very simple actions of being able to move, you know, up, down, left, right, as long as you're not, you know, at one of these boundaries which would prevent you from moving right or left or down or whatever. And oftentimes what these like the rewards in these grid worlds are, you know, you get rewarded by, you know, you might start at any random spot, but you get rewarded by getting to a particular cell, or, you know, a cell in the grid that's considered a terminal state. Okay? So you want to do that. Yeah. Oftentimes these are formulated like you want to get there in the least number of actions, as fast as possible. How do you reward something like that? Well, the way you reward it is something like this. You're given a reward of -1 for every single every transition you make, like every action you have to take. So that just keeps getting smaller and smaller and smaller as time goes on, as you take more steps. So to maximize something like this, you need to take as few steps as possible. So that's a natural reward for your objective of being able to say, like, wherever you start, like random starting spot, that you get to one of these terminal states in the least number of actions. Okay, so very simple to understand, and literally very common toy problem for reinforcement learning. So, what do policies look like in a grid world? Well, let's say you have just like a random policy, like uniformly random, in the sense of wherever I'm at in the space, I have an equal probability of moving in any of the directions. That's like a uniformly random policy. Does that look optimal or not? Yeah, not optimal, right? Because if I am right next to a terminal state, I want there to be all my probability to be concentrated on taking the one move that would get me to that terminal state. So what does an optimal policy look like in this particular grid world? Well, it's pretty simple, pretty straightforward. Wherever, just start in any one of these cells. If I start right next to a terminal cell, then it's really clear what the policy should be. The next action should take me there. If I'm not in one of those, then I need to, take a step close to one of those next to terminal states, and so forth. And that's what this policy is showing here. If you're in any one of these cells here, it doesn't matter if you move left or right or up. There is a way to go, for each one of those actions, there's another sequence of actions that will get you to the terminal state in the shortest number of actions. So these will have, uniform probability across the 3 actions here and across the 2 actions here, because it doesn't matter which way you go. You're going to either way you can still get to the terminal state in the shortest number of steps, shortest number of actions. Okay, so simple Markov decision process. Markov because it only depends on what action you take next. The only thing it depends on is where you are now. And here's the difference between some very suboptimal policy, this random policy, and an optimal policy, or the optimal policy. Okay. All right. So the whole thing here in reinforcement learning Markov decision process is just to discover these optimal policies. So how do we do this? Well, it's really easy to do this in the grid world, in simple grid worlds, because you can just enumerate the policies, and it's pretty easy to reason through it. But in these more complicated video games, what would this look like? Well, we're trying to maximize that cumulative sum of discounted rewards. And we have all this randomness to deal with. The initial state, the probability transitions, and so forth. So what exactly are we trying to maximize here? Well, because we do have probability distributions, we can't just maximize that this reward because it's going to be stochastic, meaning the sequence of rewards could be different given the same policy. So what we do is we maximize instead the expectation of that cumulative discounted sum, that series. Okay? So whatever the distributions are, so that's how we deal with the randomness in the Markov decision process. Because we say, okay, we're not actually maximizing these. It doesn't really make sense because of the stochastic nature of these sequence, the reward sequences, but we will maximize over the expectation of those. And that, like, logically makes sense. Okay, so how do we do any of this at all? Like, if you are a reasonable human being, you're looking at this and going, great, like, that doesn't help. That's just a bunch of kind of crazy math. So, so I don't really know like the history and exactly of like how all this developed, in terms of, like what things were discovered first or whatever. But the way that we, at least in what's known as Q learning, the way that we go about optimizing policies is that we're going to define a couple of helper functions here, which are known as the value function and the Q value function, and they'll be denoted by V and by Q. And what are they? Well, they are functions that somehow give us a reasonable number that represents the value of a state or of a state and action pair. So the value function V, given a policy phi, is a function that provides you this value given any of the states. And so what's a reasonable way of thinking about that? Well, it's this. What is the expected cumulative discounted sum of rewards if we start in that state and use this policy to take actions? Okay? So this is known as the value function. Notice that it's dependent on, it's a function of the state space, so it gives you a value for each state, and it's conditioned on our policy. Okay? So again, it's not really clear how exactly you would, you'd calculate these kinds of things, but it's a thing that you can write down, and it kind of makes sense, right? It's just like it's very much what we were looking at before, the expected sum here, but it's now just conditioned on, say, like the starting state. So that's the value function, V. The Q value function is now about not just like assigning a value of how good a state is, but how good a state action pair is, right? So this is exactly the same thing as before, but instead it's a function of both the state and the action, and this this sum now is the sum where we start in the state S, and then the first action we take is the action A. Again, conditioned on this particular policy. Okay, so we have these two functions that give you a value for an expression for how good a state is and how good a state and action pair are, V and Q. Now this is called deep Q learning, so we must be doing something with Q. But what exactly? Well, all this is great, but doesn't really suggest, obviously, like right away, what should be done. Well, what is done, or at least like what's done in deep Q learning, is to take advantage of a recursive formula known as the Bellman equation. So, what's the Bellman equation? All right. So whenever you see, our asterisk here, this is going like the Q asterisk here, Q star. This is the optimal Q value function. So assuming we have the optimal policy, this is the Q value function that is associated with that optimal policy. Okay? So what how do we think about this? Well, it's maximized over all the possible policies. So it's the same expectation, again, conditioned on where we start and the first action we take in the policy, but we're maximizing this over all the possible policies. So that's our optimal Q value function. And it turns out that satisfies the Bellman equation, which is a recursive formula that looks like this. What it's saying is that the optimal Q value function can be, or is a function of itself. That's the recursive nature. And how is it a function of itself? Well, it's basically a function of itself. It's saying like if I'm in this state and I take this action, SA, then the optimal thing to do from there is in the next step, which is what these primes are, the next state and action should in some sense maximize again the optimal Q value function. So what are these things, what are these R in this gamma? Well, this R is the reward that we get when we are in state S and take action A. And then this gamma sort of comes from the fact that like when t equals 1, it's like the next step here. So right, like at t equals 0, that's what this R is here. Gamma to the 0 would be a 1. So that's what this is. It's like the first entry in this sum. And then this is like the second entry in this sum, but it's really like the rest of the sum because this is again optimal. It's just like we have to discount after. So what this is saying is that once you have the optimal Q value function, then you can use it to make basically all the other, all of the other state action decisions, or like get the state updates and make the action decision using it. Notice that the policy is no longer like in this expression except implicitly through the definition of Q star. This is a way of, again, thinking about like how to choose the next state in action given the state action and reward that we just got. So so there's a way to prove this. It's fairly involved, but I'm just trying to give you some sort of like intuition of why the Bellman equation is the way it is. So what? So we have a recursive formula. So what? Anybody taken their numerical like optimization class? Nobody? Some people have. Some people kind of admit to it. Like I kind of took it. Recursive functions are typically good because they actually suggest a way to actually iteratively like compute the values of this function. And how is that done? It's done in this way. We can think about updating. We can think about producing a sequence of Q values that converge to the optimal Q value as we iterate this here. So notice what this is here. This is, I should have this. This is this equation right here. But done in this iterative way where we remove the stars. This is no longer Q star and Q star. This is like some starting point, and then this is the like the result of running this iteration. And if this function right here of Q satisfies some certain properties, this will converge, and it will oftentimes converge to the optimal thing that you want. So again, there's like a lot of cool math here, but we're not diving into that today. But what's good about this? So you could actually, you could iterate this, and you could actually, you could compute the Q star. But there's a bit of a problem here. What's the problem? One of the problems is there's no neural networks yet. So you should already be thinking there's a problem. Where are my neural networks? Where's my deep learning? But what's the problem here? What do we have to be able to do to compute this from this? Remember, this is an expectation over the state space, the S prime. And this is a max over A prime. What's the problem?
That we don't know what the next state would be given an action?
No, we do. I mean, We do and we don't. These are functions of a policy, but the policy is implicit. So, because we don't know that, we're basically going to have to compute this thing to figure out what the max is. We're going to compute it over all of the states and the actions, right? If the state space is huge and the action space is huge, or the action space is huge, this will be an impossible thing to compute, right? Like, just think about, like, if you were to try to do this for, like, even a simple Atari game, you'd have to, this would be an expectation over all the possible state spaces, right? That doesn't make any sense. Like, it just, there's too many to enumerate. So, you actually can't do this computationally for large enough, complex enough state spaces and action spaces. It's just not, it's not computationally feasible. Okay? So, how do we solve that problem? Come on, neural network people. It's now almost December. What should we do? I'm going to stay at this slide until someone just says something. Okay, how? On what?
On the gradient of value iteration that we're doing. Well, I guess we iterate in the direction of what the gradient.
So, like, yeah, we're going to do gradient descent. We need a loss. What's the loss going to be? Where's the neural network and what's the loss going to be? Chris, I appreciate you just raising your hand and going for it.
Before, when we had the expectation, we simulated that by just stochastically taking our examples.
Okay.
So is that just where you start off with the random policy and you see what happens and you take some of those examples and you
So-
grade descent based on that?
Yeah, so, okay.
That still doesn't really say what the loss function is.
Yeah, you're right. It doesn't say what the loss function is. And remember, this deep Q learning is interesting because the policy is implicit. Like, what we're going to be learning is we're going to be learning the Q function. I just gave you one of the answers. We're going to be learning the Q function, and we're going to be trying to learn we're going to try to learn the optimal one. And if we have the optimal one, we can actually, if we have any Q function, we can use it to give us our policy because it's in particular when it's optimal, it's like really clear. We just always choose the action that gives us the largest Q value. Given the state. So the policy will be implicit in this. Next time we're gonna learn about like explicit learning policies, policy gradient kinds of learning for reinforcement learning. But this is kind of like the initial way that deep learning was used in reinforcement learning, deep Q learning. So deep Q learning. So I already said it. We're going to learn Q. Q is going to be, we're going to have a neural network that's going to take as input states and actions, and will give us a value. Okay, so that's our neural network. But that's only half the question. The other half of the question is, what's the loss going to be? How can we use this right here to learn Q? Remember what we want. We want Q to be optimal, and when Q is optimal, it'll be Q star, and there should be a Q star here and a Q star here, right? But when we start off, and we randomly initialize our network, it's not going to be optimal. So these two things are going to be different. But we want them to be the same. They're different. But we want them to be the same. But they're different. But we want them to be the same. So how do we make them the same? Be a gradient descent.
The loss will be the difference between.
The loss will be the difference, almost. We need this to be a loss so that like the minimum is when they're equal. So how do we do that? You're so close. No, you're so close.
The difference between
Not just the difference, but the difference squared. Oh, that's the next one here. Sorry. We have to go all the way have to go all the way here. The difference squared. Okay? The difference squared. We want to be able to, to do this, we want in that iteration we want to minimize the difference, but for this to be a proper loss function, you need to square it. So this is what it looks like. It's a little bit nasty to kind of write down. But nevertheless, what you have is you've got your parameters theta, and they're going to have, there's an I here, but think of it as like being like t, right? Like every time we update our parameters, it's like one of these time steps. But we're going to have our parameters at like mini batch I. And what we want to do is we want to take a step that minimizes the difference between that, which is like this left-hand side, and this right-hand side here, which is what we have here as yi. Like this is just so you can write down the loss function sort of compactly, but really it's just like the right-hand side minus the left-hand side squared. And notice that we have the parameters here from the previous iteration, right? So, or from the previous mini batch. So we're going to try. The way we're going to get an update is by computing this loss, taking the gradients, and updating the parameters. Okay? Does that kind of make sense? How is this overcoming the computation problem that we said before when we were looking at this? Well, when it was an iteration where we were having to compute this over all the states and over all the actions. How is this overcoming that? One of you already said part of it, but I can't remember who said it. It was Jacob or Chris or somebody else.
It's just sampling from that state.
Yeah, so these expectations that are here, we're going to approximate those expectations with samples from the mini batch. So good. That's one of those ways. We have a max in there. What are we going to do about that? Same thing. We're just going to take max over what's in the mini batch. Okay. So, and then this is a great loss function. What we want are these two things to be the same, and by squaring them, it's the case that if we run gradient descent on this, we'll be reducing that loss closer and closer to 0, and 0 is where we want to be. So forward pass, backward pass. When we're doing the gradient update, this is the gradient of that loss there. It's ugly, but it works. You can write it down, and it works. And you can learn the policies, like the things that you saw today in those examples. You can learn the Q function associated with those optimal policies. Now, do we ever really learn the optimal policy? No. There's a lot of approximations happening here, right? Like we're approximating expectations. We're going to be approximating maxes. We're going to be approximating. We're approximating the Q value function itself by saying it's going to be equal to some neural network. It could be that the actual optimal Q value function can't be realized by the family of neural networks that we're using, right? There's no exact set of parameters that will give us that. But as we've learned, our neural networks of a particular depth and tend to be really great learners nevertheless. And even though all this will be estimates, they're really good estimates, better than most other ways we might estimate this, the Q value function, and we were able to use these very simple algorithms like gradient descent, back propagation, and iteratively update parameters and get to something that is reasonable. And that's what we do. Right. This is basically saying the thing I just said. I have to do that often. Oops, that's the end. Okay, so this is where we're going to stop today. We're out of time. we'll pick it back up, next time. We'll go through, you know, a simple example of this, and then we'll learn about some other algorithms for their reinforcement learning, like policy gradients. Okay, I'll be sticking around for the next hour if anybody's got questions about homework or projects or life. I'll charge for that though.